So this will be the last lecture I will be giving on our chapter 4 regarding the electromagnetic waves, and the name of this section will be light in matter. So essentially I will be introducing to you the macroscopic Maxwell's equations, and I will be showing what follows by this extension of our material. So essentially now, until this moment, we have considered propagation of light inside a vacuum, so inside a medium that maybe is not the most realistic of cases when we're thinking about real life. And the point is that we generalize into the macroscopic equations so that we can really understand also how materials let light to propagate inside them, and also how materials modify propagation of light. So mainly we will learn that the refractive index of a material tells us, or is a quantity defined as a ratio of speed of light in vacuum and the speed of light inside that medium. So essentially we will soon learn that speed of light is different inside a medium from the speed of light inside a vacuum. And then we will also learn in the end that the phase evolution of a propagating field inside a medium will be different from the phase evolution of the field in a vacuum. So these are the kind of few things we will learn in a nutshell, and of course a lot of mathematics will be introduced because we need to show you the macroscopic formulation. And in a macroscopic formulation we actually need to introduce quite a bit more and new field quantities, and this introduction of new field quantities was also the reason why I wanted to start with the microscopic formulation, because it looks completely way more simpler. And now in the macroscopic formulation, things look quite murky. But hopefully now, since we have already spoken about the normal microscopic Maxwell's equations, these macroscopic equations, the equations in a bulk medium, don't look that formidable anymore. But let's see how things work out. So this will be the final lecture we have, and I will be essentially considering Maxwell's equations when light is propagating in a piece of a matter. And any solid matter and also gaseous substances, they consist of numerous dipole emitters or scatterers, and that's the kind of problem that we're facing when we are trying to generalize our approach. Especially when we're looking at a solid material, and this is a good rule of thumb I like. Already a 1 cubic centimeter of a solid matter consists of a roughly 10 to the power of 33 atoms. And this means that we have a huge amount of scatterers and emitters that somehow modify propagating light. And this basically means that if you would want to treat a medium and already this 1 cubic centimeter of matter, that's the Avogadro number, incidentally, why we have this 10 to the power of 23 there, 23 there, is that we really need to do some further approximations of our problem that we can even somehow come up with means to calculate anything. Because otherwise we would have a many particle problem that would be of formidable dimensions. So essentially we would end up solving matrices that would be of the size of 10 to the power of 33 in dimensions. And there's no computers on Earth that could be trained of being able to do these kind of computations. So the solution here is to come up with macroscopic Maxwell's equations, and these in fact were the equations Maxwell was originally using. So in a way, nothing strange here. And this is the formulation. This is the formulation that helps to treat bulk medium. And how we do that is that essentially we assume that this bulk medium acts as a continuum, and then we can simplify math instead of individual sources and scatterers, so that the kind of problem at hand is being dramatically changed and simplified. And the problem is turned from a many body problem into a more of a problem that how can we calculate things, how can we estimate how the bulk medium responds to incident light. But there are many approaches, and I will be speaking of a few of them here in this lecture. So I will now get started. I will show the equations, and I will write them down using so-called auxiliary fields. I will define them later, but the equations, the Maxwell's equations, now look like in this formulation that I have the divergence of a D field. This is known as the electric displacement field, and this equals to so-called free charge density rho f. So this is quite similar to the original equation we introduced, so that the divergence of E equals rho divided by epsilon 0. It looks similar in form, but some terms look different, especially the E is being replaced with the D. The second law, the Gauss's law for magnetism, that remains unchanged, so that the divergence of the B field is still 0, and then the curl of E is still the minus time derivative of the B field, so that the Maxwell-Faraday equation is also unchanged. Then the Ampere's law, that will be modified, so we are actually not using the B field here in the curl anymore, but we are rather using the magnetizing field H. And the curl of H equals to now JF. JF is the free current density, and then we are changing our original time derivative of the E field into a simple time derivative of the D field. And we are forgetting the epsilon naught permeability naught multiplier in front of the microscopic formulation. So these are the Maxwell's equations in bulk. So the macroscopic Maxwell's equations, and rho f is the free charge density, and JF is the free current density. And here we have introduced two new field quantities, mainly the electric displacement D and the magnetizing field H, and they are defined via equations of D equals epsilon naught times E plus P. And here we also need to introduce a new kind of field quantity, source polarization or material polarization P, into the equations. And similarly for the magnetizing field H, that is being written that it's 1 over mu naught, so the vacuum permeability times B field, magnetic field, minus M, and this is the magnetization. So P is the material polarization and M is the magnetization. And incidentally, with this way of defining electric displacement and magnetic field D and H, if we would be looking at the Poynting vector, so that the S that we were introducing and speaking about in the few lectures before, this Poynting vector is also often defined using D and H. So that they, depending on the kind of Maxwell's equations in question, the Poynting vector S might look different. But in fact, it's a matter of formulation. And in this case, when we are writing the Poynting vector inside a medium, it's also a possibility that the Poynting vector may point out in a different direction than the wave vector associated with the wave propagating inside the medium. If I remember it correctly, this happens already in a normal birefringent material, or maybe it has to be biaxial, not just uniaxially birefringent. But in any case, like, we don't in fact need super exotic materials that the Poynting vector starts pointing in a different direction. But that's beyond our course. We can leave that into the future courses, more advanced courses, when you are bumping into this kind of bizarre case that S is not along K anymore. Now, what we are left in our equations is that we need to somehow combine polarization P and the magnetization with bound charges associated with the medium and bound currents. And this we can do by using equations, so that we write the bound charges rho B, that will be minus divergence of the polarization P, and then the bound currents JB are equal to curl of magnetization plus the partial time derivative of the polarization P. And this ensures that the total charges and the total currents fulfill equalities, so that the total charges are equal to the free charges plus the bound charges, and then the total currents J dot equals the free currents plus the bound currents. And these kind of equations are needed if you want to move from the macroscopic formulation into the microscopic formulation and verify that they are equivalent, and vice versa if you want to move from the microscopic formulation into the macroscopic formulation, so that we need to use these defining equations. And using them, we can show that indeed they are equivalent. I think it's a good homework exercise, so I think I will leave this kind of verification to you. For most of the materials, we're interested in terms of optics and photonics, and especially at optical frequencies, they have very small magnetic properties, negligible magnetic properties. Yes, I was able to pronunciate that difficult N word here. So that means that we really do not need to consider magnetization and the magnetic properties of the material, and instead we can really focus on the electric displacement D and the material polarization P. We do not need to worry about the magnetizing field H and the magnetization M fields as much. And this is a pretty good assumption and an approach to make, and we will do it in our course. And now, when we are looking at an optical medium, for example, a piece of glass, and we would want to understand how it responds, how it modifies the propagation of light when light is going through the piece of glass, we are looking at a problem on a macroscopic scale. We're probably thinking of a lens that has several centimeters in size, and we are thinking of things on this kind of quite macroscopic scale. And this is where it makes sense to define the material response. And the material polarization P is a quantity that defines things on this scale. So in a kind of macroscopic millimeter, centimeter scale, even on a micron scale, the material polarization is fine. But when we would want to push the kind of scope into smaller and smaller dimensions, for example, if you would want to understand how a kind of nanoscopic sized medium responds, then we start being on a kind of verge that maybe we should not use macroscopic formulation anymore, and maybe it doesn't make sense to use material polarization P anymore, but rather something else. But most of the time, this is perfectly fine. You really need to go small nanoscale optics so that you really need to do something else than just being happy of using material polarization. But when we need to kind of think, what is this guy? What is this polarization P field? We can relate this to the microscopic properties of matter. And here, the word microscopic I use to mean that I can relate capital P, the source polarization of matter, with the kind of atomic properties of matter. Because ultimately, all pieces of matter, they are made out of atoms and electrons. And somehow we should sometimes want to come up with means of being able to say that, okay, this kind of matter consists of these kind of atoms, these kind of electrons, and then subsequently I would want to calculate what kind of polarization it might have. And then we would needing to kind of connect the kind of macroscopic properties of matter with the microscopic properties. And how we can do this kind of simple connections, these, of course, these equations you should take with a pinch of salt, because it's not always the case that you can easily calculate the material polarization using these equalities, but at least most of the time you can do it. So let's introduce them to you, and I will just speak a little bit after introduction and try to warn you that sometimes this is not adequate. So polarization P, in a way, this can be defined that it's the electric or atomic dipole moment, small p, per unit volume, V. So in a way, capital P is a average dipole moment per unit volume, that kind of quantity. And if you know what kind of dipole moments we have, what kind of atomic dipole moments we have inside the medium, and we could also, in principle, just write that the polarization P, the macroscopic polarization, is N, the particle density in a unit volume, times the dipole moment. So this kind of relation would be okay. If you want to write the dipole moment differently, and this is a kind of way we often define an atomic dipole moment, small p, that then equation turns into epsilon naught times alpha, so-called atomic polarizability, times incident field. And the capital P, we will learn later how come this latter final equality is okay. the macroscopic polarization can be also written to be epsilon naught times chi, a material susceptibility, times the incident field. So alpha here is the polarizability. And here I have taken use of the fact that the atomic dipole moment small p is often defined that it's the epsilon naught times alpha, the atomic polarizability times incident field. And this is essentially a definition for an atomic dipole moment. And the kind of question mark here would be that if I have my atomic scatterer or emitter, what would be its polarizability? So this would then be the question mark, how I could calculate or how I could estimate this. And if I would know how this looks like, I could calculate the dipole moment. And if I know how many dipole moments I have inside my medium of interest and how densely they are there, I could, for example, use this equation to calculate the macroscopic polarization. So I can calculate how a single scatterer behaves or emitter behaves, and if I know how many I have them in my bulk medium, I can calculate the macroscopic polarization. And more on a kind of macroscopic framework, I can also hide these details of the microscopic properties of the material into a macroscopic parameter, so that instead of asking myself what kind of scatterers I have inside my medium, I rather just ask what kind of medium I have, what kind of material susceptibility I have in my medium, and then this would give me the relation between the incident field and the material polarization P. So there are different approaches of looking into this, and this is complicated in a way because we are bouncing back and forth between two different regimes of application. So we are thinking microscopic properties of materials. So what happens on a kind of atomic scale inside the material, and then at the same time we may be thinking of the material and its response to incident light more on a macroscopic scale. So for example, how a bulk piece of a glass responds to incident field. So there are these two different regimes, and you should be thinking about it for a while and asking yourself also always these kind of guiding questions. Am I now thinking about the kind of microscopic picture, or am I thinking about the macroscopic picture? Because that might help in you kind of constructing the information that we are trying to convey here. Okay, N was the particle density, and chi, as I said already, is the material susceptibility, and that's where the magic happens on a macroscopic scale. This is the question mark we often do not know. What is the material susceptibility of my piece of a optical material? And the relation in the beginning, the capital P equals small p divided by V, of course that defines that the source polarization, the material polarization, is essentially an average dipole moment per unit volume V. So it's that kind of quantity essentially. How on average the medium responds to incident radiation. Now working with the polarization P more on the macroscopic scale, if we would know how the material responds to incident light, of course we would be able to use the macroscopic Maxwell's equations and solve the problem. So that the P polarization really defines how the medium modifies propagation of the electromagnetic radiation. And interestingly enough, the polarization field is a quantity that in a way is also a field quantity in itself. So it's related to the propagating field. And essentially what I'm trying to say here is that the polarization field is defined via this kind of equation that I have my P, and that's equal to a dielectric function, permittivity of the medium epsilon minus epsilon naught, permittivity in vacuum, times the incident field. So essentially the polarization P looks like a field quantity, just like an incident field quantity, but it's just being modified slightly in here. And depending on the material, the modification might be minuscule, so it might behave almost like a vacuum, but it might also behave quite differently. So epsilon here is the permittivity of the medium, and that is the kind of problem or parameter we would want to solve or know when you want to look how light propagates inside the medium. And now if we have this kind of definition for a P polarization, we can now write the displacement field. and we can write it in a relation that we have the epsilon naught times E, and that was plus with P. This was the original equation we had for the electric displacement. And now we can insert into the P what we just came up with earlier. That's the defining equation. And then we can write things, the displacement field simply, that is the permittivity times E. And this is what we can use. So basically we are plugging this guy into here. And of course this epsilon naught E term vanishes here because I have something similar with a different sign here. So that what I'm left with, I have this permittivity of the medium here. So essentially now I see that the displacement field also looks like a field quantity. So it's the incident field modified somehow by the bulk material. A different way of writing epsilon would be writing it using a so-called relative permittivity. So I can also write the epsilon here, the permittivity of the medium, the dielectric constant, as epsilon naught, the permittivity in vacuum, times a relative permittivity epsilon r, and this is a unitless quantity. And that then tells me how much the material is being modifying the incident field. So epsilon is essentially epsilon naught times epsilon r. And this is also confusing, that when I know what kind of epsilon to use, I will try my best to just use epsilon naught and epsilon in here, and I always try to clarify that if I have the relative permittivity, I have the subindex r here, but some books and some authors do not distinguish, are they speaking of dielectric constant or the relative permittivity, so that they be warned that it might also be the case that in some books and some materials people might be using relative permittivities instead of permittivities, so that you might get confused if you're not careful about things. But in a way, like you should know that you should always have this epsilon naught here, vacuum permittivity somewhere, so that for example, if you have something like this, you know that this must be the permittivity of the medium, that the epsilon naught must be somewhere, and this cannot be just the relative permittivity here. Now, what we have is that we can use the helping fields, so the auxiliary fields and the material permittivity epsilon, and we can now describe propagation of radiation, electromagnetic radiation. And the nice thing about using this way of fields and their definitions is that now the propagation is basically the same as we would found already using the microscopic Maxwell's equations. And the propagation and the properties are exactly the same as long as we just replace the vacuum permittivity epsilon naught with the material permittivity epsilon. I will show you later what this actually means, this sentence, but the nice thing about this is that the field equations and the wave equations, they basically work exactly as before, but now we just replace material permittivity instead of using vacuum permittivities. And this is nice, so that the kind of structure of math remains the same. And the same thing applies for the permeabilities, so mu and mu naught, although in optics, most of the time, the magnetic properties are very small, so that we can always equate material permeability mu with mu naught. And with this change, what we have, we can directly formulate the wave equation, and we can see that now the speed of light inside this bulk medium, inside matter, can be written that it is the 1 over square root of epsilon times mu. So not the mu naught, not the permeability naught, but the permittivity and the permeability of the material. And what this means is that the speed of light starts changing depending on the kind of material properties. So speed of light in matter changes, and this motivates us to define a variable known as n. This is known as the index of refraction or refractive index, and we can define the refractive index of our bulk material, that it's the speed of light in vacuum, c or c naught, divided by the speed of light inside the medium, v. And plugging in what we have already learned, what are the functional forms of c and v, we can write the refractive index as the square root of permittivity times permeability divided by the vacuum permittivity and permeability. And essentially, most of the time, the permeability of my optical material, it's essentially the mu naught, so that the magnetic properties are weak, so that I can approximate that the refractive index is essentially epsilon divided by epsilon 0 and the square root of this. So this is the way how do we define refractive index of our materials. And this is quite nice, because now we really see how we have defined refractive index, and we are able to kind of relate them with the material properties, and these are the macroscopic material properties, so that we do not even need to know the kind of small scale, microscopic scale properties of matter. Oh, this is nice. So we have already learned something new, and the thing is that we have also introduced a new variable into the description of propagation flight, so that we have introduced the refractive index. So in other way of saying, in the microscopic formulation of Maxwell's equations, there's no such thing as there is no such thing as refractive index. There, light is always propagating inside vacuum, and it's always propagating at the speed of light, c0 in vacuum. So that in that formulation, we did not come up with a reason to define refractive index of the medium. Only when we are dealing with the macroscopic Maxwell's equations, we define refractive index as a material property. And as such, it is a macroscopic material property, because we already need to use this formulation of macroscopic Maxwell's equations. And then the final piece of information I want to teach you before I stop this lecture. So that now let's look into the kind of speed, oscillation speed, or phase evolution speed is a better word, how quickly the phase evolution changes when light is propagating inside a piece of material. So the oscillation frequency of light, the angular frequency omega, or nu could be also that one, does not really change when light is propagating inside the medium. So that it still oscillates equally fast, and this is what happens. There are some exotic counter examples, especially in the context of metamaterials and metasurfaces. People are now coming up with means that you can actually change the oscillation frequency of light when it's propagating inside the medium, but let's not speak of such kind of exotic materials right now. This is just a basic course, so we can just say that nothing changes when we are looking at the oscillation frequency of light. And in this case, we can just write equality, that the speed of light equals to the angular frequency omega divided by the k naught. That's the wave number in vacuum. And the wave number in vacuum, of course, it's the 2 pi over lambda naught, so that we can write the speed of light inside the medium, that it's the lambda naught times angular frequency omega divided by 2 pi. And now the speed of light, of course, inside the medium, it's the omega divided by k, and this is equal to lambda wavelength times angular frequency divided by 2 pi. So basically, same kind of equation. And now we can connect these, of course, so that we know that the speed of light in vacuum is associated with lambda naught omega divided by 2 pi. So this is the speed of light in vacuum. And now we know, based on the previous slide, that the speed of light is connected with the speed inside the medium via this relation, so that we know that they must be connected somehow. So that the velocity, speed of light inside the medium is lambda omega divided by 2 pi. And from here, we can solve this equation with respect to the wavelength inside the medium, so that the lambda, and we know that this is actually being modified. So that the wavelength inside the medium lambda is actually the wavelength inside vacuum divided by the refractive index. So in words, this means that the wavelength of light is actually a kind of parameter that depends on the refractive index of the medium. So wavelength of light in a medium lambda really depends on the refractive index. So it may become shorter when we are dealing with a medium. And finally, the wave vector k and its amplitude k, which is of course the modulus of the wave vector, change accordingly. So that now when we take the wave vector k, we should actually use this kind of equation, so that we have the refractive index multiplying the wave vector inside vacuum. So essentially, we have n times omega divided by c times the unit wave vector. And this is quite nice because then we can take use of the amplitudes and look into the amplitudes, how the wave vector amplitude changes, and we see that the amplitude actually grows, so that the amplitude of the wave vector inside a medium is actually larger by the factor of refractive index compared to the vacuum. And this is an equality I think you should memorize, so k equals n times omega divided by c. So what this teaches us before I move forward is that this is nice, because we can also use this when we would want to understand, for example, optical resolution associated with the microscopes, and how on earth we have such microscopes known as water immersion or oil immersion microscopes. And there we put the sample specifically inside a aqueous environment or oil environment. And somehow why we do this is that we want to increase the resolution of our microscope. And here we learn, I will speak about this later, we see here that the wave number actually increases when we have a refractive index higher than unity here. And that actually motivates that kind of instrumentation. But more on that later when we are speaking about microscopes. And finally, I'm considering what the refractive index does for the propagating wave. So let's consider a time harmonic plane wave, and let's look the mathematics, so that the E field propagating in the z direction, I have my amplitude A, and then I have my phase factor exponent I kz minus omega t. So essentially I will now replace k with the k naught n here, because I'm propagating with the field inside a medium, so that I have a phase evolution that is slightly different. So here I see that the phase evolution is actually faster for light here than what it was inside vacuum. And this is something that is actually quite important, because when we are looking into the kind of phase evolution, and we are looking into interference effects, we are looking into diffraction, we are looking into different components based on interference, we really should be knowledgeable about this, so that we must be able to calculate the phase of my field, and subsequently it makes sense that we define a quantity known as a optical path length or optical path distance, and then we must define it using the refractive index. So OPL, optical path length, is defined that it's the refractive index times z, so essentially the propagation length of my wave. And this is defined that this is the corresponding phase change that I would have for the field in a vacuum. So I define this, and I will be speaking about this later. I will use extensively this optical path length and its concept later on when I'm treating propagation, interference effects, and diffraction, but I will already define it in here. And the interesting thing here is that I'm defining it with respect to vacuum, so that depending on the medium, the optical path length is different. Or depending on the optical path length, the difference in z, the optical path length will be different. But this is a kind of equation that will be used extensively later on, so please already get familiar with it. And the final slide, almost done. For future, let's remember that realize or just you believe me when I say that the refractive index of a material, so the n parameter here, really depends on the frequency of incident light, or the wavelength of incident light. So it's not a constant, but rather it's a function that depends on the incident frequency, or I could say that depends on the incident wavelength of light. And this is of utmost importance in many cases. So this phenomena, or property, is known as the material dispersion, and this is of very much importance in optics and photonics. It limits things, it makes things possible, it makes things extremely difficult, it's always present, and most of the time as engineers trying to solve things is that we must somehow come up with means of controlling and helping out engineering material dispersion. this is most of the time the kind of main problem that we must be solving when we are working in optics and photonics. And in the next chapter, we will learn a little bit about this, that how come at optical frequencies this material dispersion exists, and how much things may change. So, of course, at the optical frequencies, the kind of physical origin that gives rise to refractive index and its dispersion, it will be the electronic properties of matter. And then it will be these that basically defines the value of the refractive index n and its dispersion. So I will be speaking more about these in the next chapter. But if you're interested in getting a more formal and a more rigorous treatment, we will be speaking also about electronic properties in our follow-up physics courses. So mainly on the course on solid state physics. And in that framework, we will be looking more also into these properties. But here, our emphasis is more in optics. So basically, we do not need to know how do we calculate refractive indices, but rather we just need to know that we have refractive indices and they are dispersive for different materials, and that's fine for us. We are more interested in dealing with light and its propagation and not how it's being modified inside a medium. So I hope you enjoyed my final lecture I had on this chapter 4. And please have a good rest of the day, enjoy the rest of the evening or the rest of the week. And soon join me in listening my next lectures on chapter 5, where I will be looking more into what happens when light is interacting with matter. So I thank you for your time and patience, and have a good one. Thanks and bye-bye.